Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. So today we are going to finish this topic right here, distributed file systems. Before we start, I have one question for you, then we'll continue and then we move on to syntax, XML, JSON, and so on. So let's start with the question to wake you up. It's 8 a.m. Here it is. With which servers must the client communicate to create a directory or to get the blocks for a file? Talking about HDFS, the Hadoop distributed file system. With the data node only, with the data node for creating the directory, with the name node to get the blocks, with the name node for creating the directory, with the data node to get the blocks, sorry for the typo, with the name node only. What goes to the name node and what goes to the data nodes? Let's take a look at your answers. Aha, the majority. So yes, this is the name node for creating the directory and the data node to get the blocks. What you get from the name nodes is the block IDs, right? Just the integer that identifies the block, but the actual blocks, the actual contents of the blocks, this is from the data nodes, right? Okay, so let me now switch back to the slides. Okay, so as a quick reminder, this is the data model of HDFS. It's difficult to do more simple than that. Well, maybe simpler than that would be object storage with S3, where it's just flat and you have key value pairs. But here you see we have this hierarchy of files organized in directories, just like on your hard called the file system. And the files, the content of the file is organized in blocks. The blocks all have the same size of 128 megabytes. You can change the default size if you want. Google uses 64 megabytes, but it's the order of magnitude that is important. What's very important is that all the blocks have the same size except the last one, because the last one might be smaller. And there is no waste of space. If the last block is smaller than the others, then it also takes less space on disk, right? Remember that an HDFS block, which is a logical thing, 128 megabytes worth of zeros and ones, if you log yourself into one of the computers, that is a data node, you log yourself there and then you peek into the local file system, you will see that these blocks are actually local files on that computer. And the size of those local files will always be 128 megabytes, except for the last blocks that can be less. All right, who is clear with this? For whom is this clear? All right, so that's the data model. So last time I stopped with how to read a file. You ask the name node for the block IDs and locations, and then you connect to the data nodes block after block. That's one way of reading, right? Block after block, you get the contents. And in Java, for example, you have a library that does it for you. So you don't even need to bother connecting to the data nodes yourself. The library is going to do it for you and just deliver the zeros and ones that are inside the file. But what I would like to show you next is how to write a file, or you create one. So who do you connect to first, the name node or the data nodes? The name node, exactly, always the name node. So you basically connect to the name node and signal your intent to create a new file. And then the name node will answer to you with an OK, saying, OK, yes, that's fine. This file didn't exist. You can create it. And here's the first block ID. So now you can send over the data for the first block. And I'm not only giving you the block ID, I'm also giving you 3 locations, 3 of the data nodes. So they are IP addresses. You know, on the internet, an IP address identifies the machine. So could be IP addresses of 3 data nodes for the first block, right? They will each get 1 replica of that first block. Then the client connects to the first of these data nodes, not all 3 of them, just the first one. And what happens is that it informs the first data node of the other 2 data nodes, but then what the first data node does is that it creates a pipeline. So the client does not connect directly to these 3 data nodes. Instead, it only connects to the first one here, and then you establish this pipeline. There is no direct connection here to the other 2, and then the block will be sent over. All right? So this is the pipeline. Now, we'll come back to that, but the reason there is a first data node is that when the name node sends the addresses of the 3 data nodes that will get a copy, it also sorts them by distance. It also says this is the nearest to you, this is the second nearest, and this is the farthest, right? So this is why you can actually efficiently organize a pipeline like that respects the distance. And then you send the data over, and by data, I mean the first block. So you basically need to send 128 megabytes worth of zeros and ones, or less if that's the only block. Okay? And then when you're done sending the data over, you will get some acknowledgement from the pipeline that goes back to you and says, yes, that's fine. We have received all of the 128 megabytes of data, everything you sent. Now, don't be scared by that. Usually I show that to computer scientists, but if you really want to know what works under the scene, you might think, okay, I ship over the 128 megabytes of data and wait for the hack. It's not quite that. There's actually what happens on the wire. So this is literally over this, over the network wire. What you actually do is send very small packets of 64 kilobytes over the network, and as many as needed to be in total 128 megabytes, right? So it's roughly 2,000, right? If I'm right, that's 2,000 of these, but these are called network packets. And what happens is that you send them, a bit like I don't know, you're a tennis trainer and you send plenty of balls to send back, and you don't wait for the balls to come back, you just continue sending them, right? So you do the same here. You keep sending packets, and then you start receiving the acknowledgements of the packets on the way. This here is very low level. It's what is really happening on the network wire level, right? That we do it like that. But in total, we will have 128 megabytes received. Okay? And then what happens? So that's the first block. And then you basically reiterate with the second block, the third block, the fourth block, the fifth block, the sixth block, and as many times as necessary. Every time you come back to the name node, say that you want to send yet another block, it replies with a block ID and with 3 data nodes. It will not always be the same 3, of course. It's different for every block. Then you organize the pipeline. You receive the acknowledgements over the network, right, in these small packets. And at some point, you're done, right? You're done. You send all your blocks. How do you know? It's because you're the client, right? So you obviously know what you want to send to HDFS. And at some point, you're done. You're out of bits to send. So you connect to the name node one last time, and you say, now I'm done, please close and release the lock. What does it mean to release the lock? It means that for as long as you're not done, normally nobody else can see what you did, right? And once you release the lock, it means now other people are allowed to see what you've done. In reality, it's a bit more flexible like that. Technically, some people might be able to start reading even though you're not completely done, but it's at their own risk, right? But this is basically releasing a lock. But what is guaranteed is that as long as you don't release the lock, nobody else can write to the same file. You're the only one. From the moment you start writing the file, you are guaranteed to be the only one to write to that file. When you release the lock, then other people might append to the file, for example. Okay? Then you close. And what happens is that once you have signaled your intention to close and that you're done, the name node is going to wait for the heartbeats. Remember the heartbeat every couple of seconds from the data node? And the name node is going to be informed in a heartbeat that the blocks have been received. And so the name node waits for what's called minimal replication, right? So the replication we want is 3. The minimal replication by default is 1. It means that the name node will wait until at least 1 replica has been confirmed for each block of the file. So every block of the file must have at least 1 confirmed replica. Once that's the case, that there is at least 1 confirmed replica, it will acknowledge to the client and say, now I'm here with releasing the lock. This is it. Your file is stored on HDFS. And in the background, it will wait until the replication of 3 is reached, right? But that happens in the background. You let the client go its own way and wait until now it's been asynchronously replicated, right? So now in many cases, you will directly get a confirmation of 3 in there, right? But you never know, maybe there are issues on the network and for some reason exactly at that moment, one of the data nodes fails and so on. But then again, if it fails, it's just going to reorganize some copy somewhere else, right? But this, the client doesn't even need to know about it. This is in the background, right? So the name node's job is to ensure that at all times, there are 3 replicas of each block. If it's under-replicated, it's going to instruct some data nodes to make a copy. If it's over-replicated, it's going to instruct to delete it, and so on and so on. Right? Any questions about this? Okay, that's the writing protocol. Now let me tell you more about the replicas. So I told you we store multiple copies of the same block. These are called replicas. There is no particular order for the replicas. I mean, there is an order when you write, but that's only based on distance. But the replicas themselves, it's fully symmetric. So there are 3 replicas. Yes? Yes, so these are what you have here is the acknowledgements block of the packets, right? The network packets that you had here, right? So these are the acknowledgements you get. And then at the end, there also is the need for the name node to know that everything is okay, right? Otherwise, at that point, only the client knows, right? But the name node also needs to know, right? It's really a matter of keeping everybody informed of everything. So this is why it needs to know that the replicas have been received in order to confirm to the client. Does it answer the question? Yep. Awesome. Okay. All right. So we have 3 copies. It's just like copies of a book, right? There is no particular copy of a book that is more important than the other, except maybe those signed by the author. But apart from that, it's all symmetric. So we have 3 replicas per default per file. You can change it. If you really want to be absolutely sure not to lose any data, you can make it 5, you can make it 10. It's just going to use more space, but you can do that, right? If you don't care, you can diminish it, reduce it to 2 or even 1, but that's at your own risk, right? If you diminish it to 1, then the data could be lost. All right. Now, I told you that the name node decides on which 3 locations you should put the replica on. The client should put the replica on. How is that decided? Well, technically, that's how. Because don't forget, you are in a data center. The data nodes are actually processes that run on machines. These machines are these nodes. These are these flat rectangular computers that are piled up on top of each other in the racks, right? So of course here it's a visual that I denotes the nodes like this, but in fact these are the rectangular piled up servers like this on the rack. So we have the nodes, they belong to the same rack. There might be another rack in the same room, and again the nodes that belong to it. And then there is the entire cluster that is made of racks. So here I only have 2 racks and 3 nodes per rack, but in fact it's more than that in reality. Now you can see that the nodes could be close or farther to each other. For example, the nodes A and B that you see here have a distance of 2 between each other. It's basically the shortest path that you can take, ignoring the direction of the arrow, right? Here, 1, 2, okay? 1, 2. So the distance between A and B is 2. Now, if you consider A and B, the distance is now 1, 2, 3, 4, right? So you can see that these are closer to each other than these two. Who agrees? Right? And the reason they are more distance really has to do with the length of the cable that you have to traverse, right? Because if you have to go all the way here, this has to go to some network switch, then some network cable across the racks, then again a network cable from the switch to the node. So there is more distance with the network. This is why it's farther away. And who says more distance says more latency, right? Needs more time to start arriving on the other side, right? So what do? There is a strategy that we have in order to decide where the replicas go. The first replica, by default, goes to the same node as the client, right? So the client stores a replica. But now it must be like, wait, what's going on here? If you come back here, the client is not a data node, right? So why am I saying that we store the replica exactly where the client is? The client is not a data node. When in fact, we will see later that the client is often also one of the data nodes. So let me just open a parenthesis for you to understand what's going on. The data nodes, we usually say the name to call the machine themselves. In fact, it's a process running on a machine, right? Just like on your laptop, you can have several processes. Maybe you have a browser open, maybe you have, I don't know, WhatsApp or whatever open on your laptop. These are several processes. Likewise, on the servers of the data center, you have a data node process that runs on many of them, and then a name node process on one of them. But there might be other things running, and we will see in the coming weeks what other things we also run on these machines. And in particular, you could absolutely be running a client of HDFS on the same machine that is also one that is running one of the data node processes. So it means that the client that you see here might actually be this machine right here, right? And in the case of MapReduce, for example, in Spark, this will actually happen. So if it is the case that this is the client that is actually uploading some data, the first replica goes exactly on the same machine because it also has a data node process on it. So it will store the first replica here. That is as efficient as it gets. It's the same machine. You don't even need to ship it over the network. It's just written to the local drive. For whom is that clear? Okay. Where did I put the, oh, over here? Okay. So the first replica is written to the same machine as where the client is. Now, it could also be that the client is not one of the name nodes, right? That could also be, then you just pick a random data node, not name node, data nodes. It could be that the client is not located on one of the data nodes. Then you pick a random data node for your first replica, any one of them. Okay, and let's call the rack on which the client is, let's call it rack A. Replica 2 will be stored anywhere really in the data center, just not on the same rack. We just pick another rack and any node on that rack, and we store a second replica of the same block. The third replica is going to be stored in another node, but in the same rack as the second one. So that not the client's rack, another rack. So it means you store a first replica on the machine where the client is, and the other two replicas in the same other rack on two different nodes in that rack. Okay? And then replica 4, if you have, of course, a replication factor of more than 3, because the default is 3, then you just kind of do it randomly, but you do want to make sure that you don't have more than one replica on every node, right? Because otherwise it's a concentration of risk, right? Klumpenrisiko. So you have at least one replica, at most one replica per node, and at most 2 per racks. If you already have 2 replicas on the same rack, then that's enough. You shouldn't have more than 2. Now let me give you an intuition of why we use that strategy. So that's an example. I'm going to remove the chat toolbar in the lecture hall so that you see. Otherwise, it's hiding. There you go. So you see, the client is here, and on the same machine, there's a data node process. We store the first replica here, and replicas 2 and 3 on another rack, the same rack, 2 different nodes. So this is first replica and second and third replicas, right? This is how it's done. And then we do it again with more and more and more blocks as they come. So every time the first replica is going to be stored here and the other replicas on some different rack, but it might not be this one every time. It can be another rack for the second block and so on. Now, that's going to happen. We have the 2 blocks here, the yellow and the green blocks. So the first replica of each is stored on the same machine as the client. Then we have a rack that stores 2 copies of the yellow block, and here another rack, C, maybe that stores 2 copies of the green block. So you see that it kind of gets spread over the cluster, right? The different blocks are stored at different locations, right? Now, of course, if the file is very large, that will not all fit on the same machine. Then at some point, you might not be able to do that, right? But if the file is small enough, then it makes sense to store it on the same machine. Okay. Now, you might think, why do we store replicas 2 and 3 on the same rack, but another rack? Why, for example, we could have considered another strategy. Why don't we say we store the second replica on the same rack as the client? Right? We store the first replica on the client, and the second replica, same rack as the client. Then the third replica, another rack. But you see the problem here. If we do that, then we are going to start concentrating the blocks in the same rack. And you know that when things fail in a data center, they tend to fail at the same place, right? So for example, you might have in the rack some electricity short circuit or some network switch that goes down, then the entire rack is down. So you don't want to concentrate all of your risks in the same rack. So this is why we are not doing that. We prefer to do this, okay? It's a bit safer. Everybody with me? Who is following? Okay, very on Zoom too? You're following on Zoom? No? Everything is fine. Okay, very good. So now, there is a problem with that system. The problem is that for the data nodes, it's fine, right? Everything is distributed all over the cluster. So if we have nodes that crash, we're going to be all right because we have more copies somewhere else. But we have a problem with the name node because what happens if the name node fails? So we need to understand what's going on in it, right? So I need to show you what's stored on the name node. What do we lose if the name node fails? So the name node, we saw last time, it stores 3 things, right? It has the hierarchy with the directories and files, the names of the directories and files. Then it has a mapping from each file to the block IDs, right? That I use colors for, but it's block IDs here. And then for every block ID, you know the IP addresses or the locations of the data nodes that store a copy, right? So if the name node fails, and there's only one of them, this goes away. All of that is wiped out. Now, do you understand that if this is wiped out and we lose that information, we basically cannot read the data anymore? Because we might still have the blocks, but it's like a giant puzzle, right? You don't know how to reassemble the blocks together. Who sees that? Right? We need that information in order to recover the data. So what does it mean? If we can lose data and we're afraid of losing data, we do a backup, right? Just like you do for your laptop. So we do a backup, we take this, and we back up to some storage. It's typically a network attached drives or there's technology in the cloud, but it's not going to be HDFS, of course, because otherwise you're basically sewing the branch on which you're sitting, right? So it cannot be HDFS, but it will be some sort of network attached drive. And we store the contents, what is in the name node's memory, to a file that's called a namespace file. We take a picture, like a snapshot of what it looks like and store it as a file on that storage, on that drive. Now we don't store everything. We, in fact, only store the first 2, so the file namespace and the mapping from the file names to the block IDs, but we do not need to save the location of the data of the node, sorry, of the block IDs on the data nodes. Why do we not need to save that? Yes? Exactly, you can recover it from the heartbeats. So if you lose that, that's okay. You just wait for the heartbeats and you will know at some point where it was sitting. So you can save yourself from space. You can just not save that. You don't back up that, but this you back up in a namespace file. So this is at a certain point in time, you take a snapshot and you store the namespace file. But now, after you've taken the snapshot, people will create directories, people will create more files, people will delete files. So the whole thing has a life, right, of its own. So then the namespace file that you've saved an hour ago will no longer be up to date. It's going to be stale, right? It's as if the last backup of your laptop was 1 month ago. Everything you've done in the past month would be lost, right? So what you do is you keep a log, just like on the captain on a ship, right? You keep a log of everything that's going on. So once you have taken the snapshot, namespace file, you log and write down every update in the order in which it's done, every update one after the other in some edit log. So you keep appending, like at that time on that day this happened, at that time on that day this happened, and the edit log is going to grow bigger, right, as more things happen. Now, all of that, if you want to be even more extra careful, you are going to extra back it up to even more places, right? So that was on a network attached drive. Now you might make a copy even on S3, on some tapes in a warehouse. So to be extra sure you don't lose the data. Typically, it's going to be cheap to do this, okay? We just make copies, all we can of these things. Now, we can answer the question, what if the name node fails? So imagine it fails. So obviously, we need to start it up again. So let's be optimistic and assume it's not a hardware failure and we can just restart it. Otherwise, we replace the server with another server. But then we start it up again. How much time do you think it's going to take? Let's say in a standard system. Who thinks 1 minute? To get HDFS back up and running? 5 minutes? 2 minutes? 10 minutes, sorry? 30 minutes? 1 hour? Okay, are you close to the truth? So typically, it's going to take 30 minutes, right, as a rule of thumb. It's, again, the order of magnitudes. So what happens is that you take the namespace file. It was a snapshot, so you just make a copy again in memory of that snapshot, right? So you have the file hierarchy and the file system. But that's the old as it was at the snapshot time, and then you need to play the edit log. So you go through the edits and apply them one by one. Just like who does music? Who knows about MIDI sequencers? This is exactly the same as when you have music that is recorded as events, like you press that note for that and that long, and you just go through the edit log like a sequencer and just play the edits and apply them there. And when you're done through the entire edit log, then you have recovered the whole thing, right? So the entire file namespace plus the mapping to the block IDs. And then for the mapping to the data nodes, as you said earlier, you just wait until the heartbeats arrive, and then you will know at some point. Now we have done that. And again, that whole thing can easily take 30 minutes. Can you tell all of the employees in your company that now they have to wait for 30 minutes every time something like this happened? Probably not, right? Because that would be, imagine you have 1,000 employees and everybody needs to wait for 30 minutes. It's too costly. You cannot do that. So we need some solutions. And there are solutions to this. So can we do better? Yes. One way to do it better is to not let the edit log grow too large. Because if you wait, at some point, the edit log is going to be gigantic, right, as you apply changes. So once in a while, you just merge the edit log into a new snapshot, right? And then you have a larger namespace file, but now the edit log is empty again, right? And so if it fails, you load back the namespace file in memory and then apply maybe a smaller edit log, right? So what's important is that if periodically, at regular intervals, you merge back the edit log into the old namespace file to create a new, more up-to-date namespace file, then you can keep the size of the edit log under control. Because again, the larger the edit log, the more time it's going to take to play it. Okay? So you want to periodically, it's called the checkpoint, periodically save it. Now, what we also do, and there's a whole history over the years of how this evolved, what we do is that we also have what's called a standby name node. A standby name node is a little bit like the vice president of the United States. So if the president can no longer act, then the vice president takes over. It's exactly the same thing here. The standby name node is really to take over as the name node if that happens, right? So what it does, the standby name node, is that it is in the background. It receives exactly the same input as the name node, so it knows everything that's going on. It keeps in its memory exactly the same structures, the file namespace, the mappings, and even the mappings from the locations to the block ID to their locations. It's just working in the shadow, ready to jump in. And if the name node fails, the active name node fails, then the standby name node immediately takes over. You don't need to wait for 30 minutes. It already has everything it needs to function. Who sees that? All right, awesome. Now, if you try to Google things a little bit, you will see a lot of other names, like standby name node is one of them. You will see secondary name node, backup name node, checkpoint name node, and so on and so on. View it as archaeology. It's just that over time, there were multiple versions of this whole thing, and every year they came up with an improvement and they give it a new name, right? So now, one of the most up-to-date is the notion of standby name node, that is allowed to take over from the name node. The previous versions could not take over. They were more like for backing up. But this one can take over. All right, and you see the namespace file and edit log, they are in some drive, network attached, so both of them can access that drive, right? Okay, now even more recently, there is yet another one that we call observer name node. That is yet another version of that. So I'm only going to tell you about the standby name node and the observer name node. The other ones you don't need to know about. So what does the observer name node do that the standby name node cannot do? What's new about it? Well, the observer name node, in fact, is not just standing in the shadow doing nothing, except replicating the data. It is also allowed to deliver on read requests, meaning that the clients connecting to HDFS, if there's a lot of them suddenly that connect and the name node, the active name node is overloaded, then it's fine to also connect, that the clients can also connect to the observer name node to read things, only to read things, not to write or anything. For writing, it's only the active name node. But to read things, you can connect to the observer name node. So the idea is to take off the shoulders of the active name node some of the workloads for reading data. Okay, yes?
So once standby, because the name node, it says the name node until it's crashed, or when the original name node is back online, it gets back the control.
That's a good question. So you could imagine the two strategies, right? So if at some point the name node crashes and then it recovers, you could have two strategies, right? You could say, okay, then the standby name node gives back control to the former active name node. So you could do this. But on the other hand, why would you, right? You can just continue, since the standby name node already took over as the active name node, you can just let it continue, right? And then the active name node, the formerly active name node that recovers, then would act as the standby name node, right? So there is more efficiency in not swapping again, right? You just keep the roles swapped. This is where the analogy with president, vice president stops, right? Okay, so, right. There's yet another thing that you're welcome. There's yet another thing that the engineers of HDFS, again, every year they work on new features. They came up with this federated distributed file system. Who already installed Linux on their machines? Okay. Have you also gone through the partition process of allocating to your drive the partitions? Do you remember that here you have the slash that is the root of the drive, and then you have /home, you have /user, and so on, and you can allocate them to different partitions, right? For example, the home directory or the root directory could be someplace else. Here it's exactly the same thing. You could, in fact, have a federation of name nodes, just like the United Federation of Planets, right? So you have all of these name nodes, but every name node is responsible for a very specific directory, just like /home, /root, and so on for Linux. So you assign. So if you have /foo access, then you connect to the name node in charge on the left. If you want to access data in the /bar directory, you connect to the one on the right. This is called federated distributed file system. And again, similar to partitions when you install Linux. Okay. So I have now a few yes, go ahead. So that I'm not knowledgeable enough to give details on that, but I would imagine that there is some federated DFS protocol that makes sure that they don't step on each other's feet, right? In terms, so they know where there is available space and so on, right? Does it answers your question? Yeah. Okay. All right. So now I'm going to finish on a few very practical considerations, like how do you use HDFS? Because so far I just told you how it works, but how do you use it? And the answer is, it works pretty much like connecting to using your hard drive on your computer. Who of you already used the command line? Okay, so you're familiar with that. So you know that in the command line, you can type commands. So if you're on Linux or Mac, ls to list the content of a directory, cat to display the content of a file, mkdir to create a directory, and so on and so on. On Windows, it might be slightly different. Like you might have, I can't remember exactly, but dir, I think, to list the contents of a directory instead of ls. But the idea is the same. You type things. Well, that's the same actually for HDFS. You also type things on the command line. And in fact, what you type, going to give you the standard version, what you type is always Hadoop FS, like file system, followed by the arguments. And the arguments will be similar to this ls, cat, mkdir, and so on in there. Now, there is also a command called HDFS, but not a lot of people use that. The idea is that Hadoop is more powerful. Hadoop can write on HDFS. It can also be used to write to your local file system. It can be used, yes, to write on S3. You can also do it with this command line utility. So technically, this is the reason why not many people use that one, because this one can do more. It can connect to many more places. So Hadoop FS. And here are a few examples. Hadoop FS -ls does the same as the ls command in Linux or macOS, right? Hadoop FS -cat, it displays on your screen the content of the file. And that's the same as the cat command that works on your laptop. rm is remove directory. Again, you have it for your local file system. But if you say Hadoop FS -rm dir file, that's going to remove this directory. mkdir to create and so on. So you see, this all follows the standard that everybody knows that's called POSIX. So it's not exactly, but it's more like POSIX-like, right? It's very, very close to POSIX. So basically, if you're familiar with the command line or Linux or macOS, you will have no problem using HDFS because it just is exactly the same commands, just with a dash and with Hadoop FS in front. But there will be one difference. There will be one difference because if you try to type these commands on your laptop, on your local drive, you press enter, it's going to be instant. This for if it's a small file here. It's going to be instant. You press return and you see the results. Not so on HDFS. If you actually do this and you are connected to HDFS and the slash is really bound to some HDFS server, this will take more like 1 or 2 seconds. So you're going to press ls, then it will be hanging for 1 or 2 seconds and then list the contents. You say cat, again, 1 or 2 seconds, and it displays the results. rm, again, 1 or 2 seconds. So you will notice that it's actually slower. And that slower is actually latency. It's because it needs to connect to the name node, to connect via the network and wait for an answer, and maybe connect to data nodes and get the blocks and get an answer. So it's because of the latency that this is slower than a local file system. But the commands themselves, they are very similar. So now there are also commands to upload and download, because if you have a file system remotely on HDFS, you obviously will want to upload some files in there and maybe to download some files in there. Of course, that only works for small files, right? If the file sits on your laptop, it means it's small enough to be on your laptop, then you can upload it to HDFS. If you have a file on HDFS and it's small enough, then you can download it to your laptop. It's obvious that you cannot download a file that would be 100 terabytes, right? Because you can have files that are 100 terabytes on HDFS. But then it's obvious you cannot download it. It would not fit on your machine. But if it fits and you know you can download it, then you can use this copy from local and copy to local. So copy from local is to upload. So you upload local file 1 and 2 into user Hadoop dir, something on HDFS. And the other one is downloading, right? Hadoop FS copy to local, it's downloading that file to a local file. Again, assuming that it fits on your hard drive. Do we have a question? To copy? You mean as opposed to copy on the SCP or CP on Linux? Yes. That's a good question. I assume it has to do with physical implementation, that splitting into two different commands made the architecture easier in terms of what it does. At least this is what I would assume. Because otherwise, if you have copy, the copy from HDFS to HDFS or local to local would be different. So I assume it's more optimized like this. That would be my guess. But you could have imagined, right, that you have a single command that is CP and that takes care of it. So I assume that it's more optimal. Okay. That I'm not sure I should show you because that's actually scary. It's just internal configuration stuff. So you don't need to understand that. It will be actually XML syntax, just telling you. But basically, these are configuration files that most people will not ever see in their entire life, but maybe the sysadmins who configure the cluster will know about this. It just allows you to control a few things. For example, here, when you connect, when you have just the slash, it tells you the default server, the name nodes that the slash should be interpreted as, right? So it tells you where your HDFS server is. And then you have, you can have the replication factor that you can set to whatever you want. For some reason, somebody set it to 1 in here, but anyway, by default, it's 3. And then you have the location of the directories of the data nodes and name nodes. So this is the local file system of each name node and data node. If you would connect to it manually and you would go in there, then you would see the actual blocks, right? But again, you could probably forget that. If that confused you, then forget these 2 slides. This is just sysadmin stuff. Then we have a few utilities that people use in conjunction with HDFS. One is Apache Flume that is meant to aggregate log data. Log, for example, your website log, who connects to your website, who accesses what, and so on. So Apache Flume is good into collecting logs into HDFS. Right. Another one is good at importing from a relational database. So you have a relational database, and it's just going to copy it over and move it over to HDFS in some format that makes sense. You could imagine CSV or others, but basically it copies over Apache Scoop from a relational database into HDFS. Why do we want that? Because we're going to want to analyze it. That's why, right? But that we'll see a bit later. Okay. And final words before the break. I told you about terminology. I warned you that there's a lot of words that kind of mean the same thing. I gave you the example of block, chunk, split, partition, shard, and so on and so on. They all mean the same thing, but in different contexts, we might use different words. So you see block in HDFS is called the chunk in GFS. A name node is called the master in GFS, the Google file system. A data node is called the chunk server on GFS. A namespace image is called the checkpoint image in GFS. An edit log is called an operation log in GFS and so on. But you know, it doesn't really matter what you call it, right? Well, it matters so we communicate with each other because we need to speak the same language. But in the end, the technology is very similar, right? So again, the Google file system is the original one back in 2004, and HDFS is the open source version of GFS, okay? Something else is the block size that can change. It depends on the distribution, just like there are Linux distributions. We also have HDFS distribution. Cloudera is one distribution. Apache HDFS is another distribution. So there are several of them. And of course, when you install it, it comes in different flavors in the way that it is configured, right? So some will use 64 megabytes, some others 124 megabytes, 28 megabytes. And as I told you, in the case of Azure, they were bold. They went all the way to 4 gigabytes for the blocks, which is actually quite large. They even made a huge announcement about that a while ago. Okay. And I'm leaving you with a few links. If you are interested in the documentation, that's actually quite interesting. So of course, there's the textbook that I wrote, but if you're interested, you can also look at that. The GFS paper and the HDFS paper can also be available. It's an optional reading, right? The GFS paper, did we put the GFS paper on the website? I see. It's only if you're interested, right? If you want to read about it, but for sure there is the HDFS paper. And then the Java API is for the people who want to connect to HDFS with Java, would be interesting. But again, many people will just use the command lines, or they will use MapReduce or Spark to actually use HDFS. Okay, so this is HDFS. So now we have S3 to store objects, flat list of key value pairs. We have HDFS, that is a hierarchy of files that are organized in large blocks, right? There is a big difference between the two, is that S3 or Azure Blob Storage or Google Cloud Storage, these are services, right? You pay maybe something and then you access the service. HDFS is something you need to install, right? You need to provide the servers, you need to install it and so on. Of course, you can also have one-click installs that you connect to Amazon and it creates one for you, but it's still going to be servers that belong to you. So this is a major difference between a worldwide service on the one hand and a local service, a local installation to your company. And there are many different HDFS clusters in the world, one per company typically. Okay, so this brings us to the break, because I see that it is 9 a.m. and even it's 1 past, so I'll give you the extra minute and we start at 16 past 12, and we'll talk about syntax. We'll start storing things on HDFS and S3. Thank you very much.